Okay, so let's go over our calculations for the lab that we did yesterday. The purpose again of the lab is to find what's going to be a very important standard number for us. What is the volume if I have 1 mole, that quantity of a gas, and remember, all gases would have the same pressure and would occupy the same volume regardless of what gas it is. So it'll be important for us. What is 1 mole of a gas? And let's use our reference conditions, standard temperature and pressure. I've kept these up. I got a little reflection on the board, but I think you copied them yesterday. The room temperature we had, room pressure we had, the vapor pressure of water at this temperature, and then what is standard temperature and pressure? Standard temperature and pressure is 273 Kelvin. Or 1.0 atmosphere. So under those standard conditions that we set as a reference point, what would 1 mole of a gas occupy under those conditions? And we're going to find that with this lab calculation. So this was the reaction that we did, right? We collected, but when we collected over water. So in addition to the hydrogen gas that we collected through the reaction, we also had some water vapor. We got to get the partial and subtract the partial pressure of water vapor out of that, because we're really interested in the partial pressure of a hydrogen gas, how much hydrogen gas was in there. So total pressure I got from the room pressure, 748. That had hydrogen gas, subtract out the vapor pressure of water, and I get 728.5. So all groups should have that as your partial pressure of water, 728.5 torr. Now, the second part said, part 2, what volume of gas would you have collected in your tube had that been under standard conditions? And here we're using our combined gas law, P1 V1 T1 equals P2 V2 T2. I took the N out because the particles are not changing. And so I've got my P1 is going to be the partial pressure of the hydrogen gas, not the total pressure. Partial pressure of the hydrogen gas. V1, I just made up a number, right? I saw some of yours, and so 41. Use your data for that one, for V1. T1 will all have the same number. The room temperature is 21.7. Add 273, we got to be in Kelvin for gas laws. So what I did is I plugged those in. Now let's put that up here. So I'm going to erase my numbers over here. So I have 728.5 times 41 over 294.7. And then, so what's my P2? P2 would be standard pressure. What's standard pressure? 1 atmosphere, but I'm in torr. 1 atmosphere, the conversion we have is 760 torr. Right, so be careful, I'm in torr, so the standard pressure, 1 atmosphere is 760 torr times V2, that's what I want to find, divided by temperature under standard conditions, 273 K. That's my standard temp. I multiply that through, and if I did this right, I got V2 equals 36.4 milliliters. So that's my V2. A little bit of a reflection going on my board, but so there's V2 for this. Fix that. A little bit better, maybe? Okay, what is V2? That is the volume of hydrogen gas, the amount of hydrogen gas I had that would have occupied had this not been under our room conditions, but at standard temperature and pressure. That number looks okay to me. Check my calculations. Well, use your numbers because the pressure in under standard conditions slightly greater, which would squeeze it into a smaller volume. Temperature slightly smaller, so at the same pressure that would have to be a little bit smaller volume. So that number looks okay to me. So there is V2, the volume that it would occupy under standard conditions. That's number 2. And then number 3 says determine the mass and then the moles of magnesium used. We used, so I gave you that it was 0.0200 grams per centimeter. I'm just going to go with 2 centimeters. So that would be 0.0400 grams. Convert to moles, 1 mole. Magnesium, 24.31 grams, has how many moles are in 0.0400 grams? Quick calculation. And I get X equals 0.00165 or 1.65 times 10 to the minus 3. What are my units? Moles. So now I know how many moles I reacted, and I know that that's how many moles of magnesium, 0.00165 mole. Because the coefficients, 1 magnesium makes 1 hydrogen gas, I know in that tube there was 0.00165 moles of hydrogen gas. So I got a known quantity of gas at a known volume under standard conditions. I'm getting close to what our goal was. Okay, what if I had 1 mole, right? Not 0.00165 mole. If I had 1 mole, what volume would that occupy at under standard conditions? So simple ratio. Let's work over here. If this quantity of moles, 0.00165 moles, occupies 36.4 milliliters, 1 mole would occupy X, I'll just put X, or V, the volume of 1 mole. I could flip that. And my number's not bad, 22.06, 22,000, sorry. Sure, I'm still on camera. That's an important number, so let's bring it over here. That's what I get. So, all right, milliliters per mole of gas. According to this calculations and our lab calculations, if I had a mole of a gas under standard conditions, it should occupy 22,060. We're pretty close. It's actually 22.4 liters. Whoops. Let's change it to liters. 22 divide by 1,000 to put in liters. 0.06 or 22.1. Let's round it to 3/6 liters. Based on what we did in the lab, if you have a mole of a gas, it should occupy 22.1 liters. The actual number is 22.4 liters. Right? So we came pretty close, depending on where your data is. That's our target number. We didn't hit too far because I think the numbers I used were close to your lab numbers. So let's work with that. That's going to be an important number for us as we go forward. Notice though, so well wait, that's hydrogen gas. What if it was a mole of oxygen gas? Same thing. The pressure and volume of a gas depend on the amount or the quantity of the gas, not on what gas it is. So that's a standard reference number that we will continue to use going forward. There was something on percent air. I'm going to let you guys do that, and the other questions to try that. So let's get to here, and then from here we can start to jump off and really work with that number and continue our journey through gas laws.